Okay, so let us start our sixth lecture on power system operation and control. This is again, I'm calling this as an introduction lecture. Probably this is going to be our last introduction lecture, and thereafter we are going to start a bit of a more technical. We'll start with first optimization, basic of optimization, and I'll tell you today, later today in the class, that what is the need of optimization in this course, and then later on we'll learn about optimization in 3 or 4 lectures, and then we'll come back to the power system applications, and then we'll start those. We'll try to learn all those things later on. Okay, so just a quick recap. We saw about security analysis. We saw how these security and reliability are different, what is exactly in danger, what happens at the control center, what all are the features. There are 3 features: monitoring, security analysis, and security enhancement. We have seen the brief of it, and obviously we'll be seeing a detailed on basically security enhancement. This security constraint optimization, this we'll be seeing extremely in detail. There are 2 lectures down the line I have scheduled where I'll be explaining you detail, because theoretically it sounds good. Yes, you can easily see and visualize, but mathematically how you are going to do it, how a control center does that thing, that is very interesting to know, and how they do it. Okay, so we were discussing this yesterday at the last, and this is basically operating states of power system, and we were discussing that how these operating states looks like, and how it has been initially proposed by D'Liaco, and then it was modified by Stott, and we have seen how these arrows work. So just to give you a heads up, all the downward arrows, like this arrow, this arrow, this arrow, this arrow, is basically telling you that there is some disturbance or some contingency, and all the upward arrows, I'm marking them as blue, are basically some control action which is bringing the system back to the normal state. Okay, so from this, let us see all these 6 blocks one by one, and what exactly happens in these 6 blocks, and basically that will give you understanding what is the criteria, how we categorize our system into these 6 blocks. So let us start. Let me quickly number them. So I have numbered them here: 1, 2, 3, 4, 5, and 6. There are 6 blocks. I have numbered them. So a quick background before we start is, if you see 1, 2, 3, these 3 blocks, there are no limit violations. So limit violations, when I say, in power system, you have some of the limits which you have to ensure. So can you tell me what all limits what we have to ensure from in a power system? Can anybody guess that?
Power, active power and reactive power
Of
of a generator and the line that can be flow.
Okay, good. So let's say real power flow and reactive power flow. Good. These are the limits which we want to ensure that it should remain within a specified, or there is a, because these are mechanical machines and mechanical wires, so there are mechanical limitations beyond which it will not operate, or it may get damaged. Right? Any more limits which we want to ensure?
Voltage magnitude and frequency.
Good. This is also good. Or let me write it in terms of delta. 1 second. Yeah, let me write. Maintain this consistency that it will be delta. So voltage magnitude is V and delta is the angle phasor of that. Any more limits?
Diameter of AVR.
Which one? Sorry.
Parameter of control. The parameter.
Parameters of control.
Yeah, control. Yeah.
Means okay, just to so from the steady state point of view, only these are the 6 constraints which we want to ensure. Also, if let's say you want to add there, you can also tell the real and reactive power demand has to be within a particular limit, because if the demand fluctuates, all these things which you have told, PGQG, PFQF, V delta, all these will vary if the demand is changing. So we want all these limits to remain within a specified bound. So everything will have some minimum limit and some maximum limit. Minimum means I'm writing an underline, and maximum I'm writing a overline on this circle basis. So there will be some underline and overline, minimum and maximum limit of all these states or parameters. So PGQG is coming from the generators. So PGQG is basically limits of the generators. And how does a generator decide its limits? Do you know that? How a generator decide its limits?
If the generator want to decide the RT4, we use the governor for that. And for limitation of Q, we use the excitation system.
So you mean to say PG from the governor you mentioned, and for QG?
Yeah, QG for excitation system.
Excitation system. Okay. But governor and excitation in combination, it leads to a curve. Do you know the name of it? You are right. Those actually governor controlled and excitation control limits the PGQG, but there is a term for it. So have you heard about capability curve?
Yeah.
So if you see, for all the generator, there is a capability curve of a generator. So whenever you draw in x-axis PG, y-axis QG, so there will be a lot of limits, not just one. There are armature current limit, there are excitation current limit, there are vibration limit, because generators may vibrate if the flux inside or magnetic flux inside a generator is extensively huge, then it will vibrate. So there is limitation on that. There is a limitation on the stator current, there is a limitation on rotor current, there is a limitation on what is remaining. I think all these currents, and as well as voltage limit is also there for the terminals, and the voltage limits of the how much maximum voltage the stator and rotor can take. So all these limits in combination will lead to a final curve, and this curve is actually known as a capability curve. So if let's say you want to utilize a generator for the complete real power means you are here only at the x-axis, that means you cannot generate or consume reactive power from this generator. If you are operating at this point of PG, then you have this much QG min. So the top is QG generation, the positive, and the negative is QG absorption. So QG can be consumed when it is negative, QG is generated when it is positive. So PG decides how much QG you can generate from a generator, or you can consume from a generator. If the PG is very less, then obviously you have a huge margin of QG absorption and generation, right? So this comes from the capability curve, right? And just for your information, because in the next semester you will be studying about the power system deregulation, where we'll talk in terms of economics of power system. How does economics of power system works? Economics means obviously because power plant is built either by government or by the private players, and all those private players are basically businessmen, right? And if a businessman is investing on a power plant, if they are taking a loan, if they are going for the contract, buying a land, purchasing the coal mines, probably if it is a coal-based thermal power plant, or purchasing a diesel. So it involves huge amount of money. And if a businessman has invested this much huge amount of money, he will expect some return or some amount of profits. If he will be definitely expecting, otherwise nobody will invest in this business, right? So like for example, renewable energy, a lot of people are now investing in renewable energy. Even rooftop solars are coming up. Even people like in apartments and residential complexes, even in the commercial buildings, everywhere people are installing rooftop solars. So obviously people are seeing some financial benefit. Nobody worried about the voltage and frequency. That is mostly that is a secondary part. The first thing is always that you should get a monetary benefit, right? So whenever that type of thing happens, whenever you are thinking of monetary benefit, this capability curve tells the generator that if he decides to generate this value, then how much QG he can provide to the system. And QG is directly linked with the voltage. So if the QG absorption and generation limit is less, so you know from the power system analysis, I'm sure you must have studied in your bachelor's, that if if a generator hits or reaches its reactive power generation limits, that means it is no more a PV bus. Means I'm sure you know this from power flow, that it is no more a PV bus. It converts from a PV bus to a PQ bus. You have this idea, right? PV bus and PQ bus, slack bus, these are the three types of buses in power flows. And so if the reactive power generation hits the limit or reaches the limit, then it no more remains a PV bus, it becomes a PQ bus. Why it does that? Because it loses the control of voltage. It is no more that type of generator which has reached its reactive power generation limit. That type of generator cannot control or set the voltage at the connected bus, obviously because he does not have reactive power margin with itself remaining. So therefore it becomes a PQ bus. So that is the thing. So just wanted to connect you with how PGQG is decided. And another thing is PFQF. This is again coming from the manufacturer ratings. Every manufacturer from wherever we are purchasing the transmission lines, they give a manufacturer rating that how much is the capacity of the line, how much maximum current it can take, how much power it can take. And then there is a voltage angle and magnitude range where it should remain within that range. Otherwise, and this is decided by the regulator or the standard set by a system operator, that you have to maintain a voltage within a particular range. And this PDQD is generally decided by a forecast. There are many factors obviously, but just to give you a quick idea, it is generally decided by a forecast, and whatever is the forecast, we have to maintain the PDQD within that forecast range. So forecast will also give you a small range, and we expect that PDQD should remain within that forecast range. For example, let's say every state in India, means India has a lot of around 20, I don't know, I think 29 or 30 states right now. So all those states have internally state electricity boards, and even so every state decides the forecast of their own load, and then inside the states there are state electricity boards. For example, in Uttar Pradesh there are 5 electricity boards, and in Rajasthan there are 3, probably in Delhi there are 3. So there are different electricity boards in each state, and then each electricity board decides the PDQD of their own consumers or their own loads. So this is the way they fine tune the forecast, and they basically go on to the lower level and decide that value. So obviously the load has to vary within a range, because if they vary beyond that range, and because you are making all the planning of PGQG, PFQF, V delta based on this variation of PDQD, but if this variation violates, then it is a problem for PGQG to maintain, or some or the other limit will violate. So basically we are talking about, when I say that in 1 to 3 blocks, all the limit violations, that means there are no limit violations, that means all these parameters are within a specified limit, they are not violating. I hope it is clear. Now in 4, 5 and 6 there are some serious problems. There are some, or let me make it with different color so that it gives an idea. So this, let me make it by red. So this 4, 5, 6 will have some serious problems. Some problem is there which has led to the system to come to this state. Okay, so this is the base case underlining. And also one more thing, that the load generation balance means whatever sum of PG should be equal to sum of PD plus P loss. This is always satisfied in all these 6 states, right? This is assumed, and this is also not only assumed, it is also ensured that because it is ensured, that's why we can easily assume that factor, that sum of PG should be equal to sum of PD plus P loss. That means load generation balance is always there in all 6 states, all 6 blocks what you see here. Okay, now with this, let us see all these blocks one by one. Now let us talk about the secure state first. Now what do you imagine here in the secure state? What is happening here? Can anybody guess that?
I think all parameters will be in steady state case. The derivation is continuous.
Sorry, there is a lot of background noise. I'm unable to hear. All the parameters I am unable to hear. Anybody who can hear, if they can answer.
All the states are in all the states are in a limit and in a specified limit in the secure state. There is no variation is there.
Okay, good. Yeah, exactly. So there are no limit violations, just to give you, because as I mentioned earlier. And also, whenever we talk about no limit violation, I also mean if, let's say, there is a single credible contingency. Credible contingency means a contingency which can make the system damage, or basically it can lead to some or the other limit violations, even if those single credible single, why I am saying single, because most of the power system just work on n-1, as I mentioned this on our previous class, that n-1 is ensured. So that's why I'm saying single credible contingency. So if any single credible contingency takes place, even then there is no limit violation in the secure state. Clear? So naturally in the system there is no violation, and also even if a single credible contingency takes place, even then there is no system violation or no limit violation. Clear? Now practically, if you can imagine the size of the system and the size of the load, we are working in more than we are consuming more than 170 gigawatt of peak load, or even you can imagine if you talk about average load, it is somewhere around 150 gigawatt. It's huge amount of power. And obviously all the states, all the different states have different features, like Uttar Pradesh is having a lot of agricultural state, Chhattisgarh is having agricultural state, even let's say if you talk about Mumbai or Maharashtra or Karnataka, they are more of an industrial state or corporate state. Tamil Nadu is having an industrial state. So all these states have their own features and operating features. Everything is keep varying, and even then in that varying situations, if you are able to maintain that there is no limit violation, then we call it as it's a dream state or it's an ideal state. And practically it is very rarely possible. Obviously things are continuously varying. It is difficult to visualize everything working perfectly without any damage. So it's a very rare condition. Now Another important point here is, as I mentioned in the previous class, preventive actions. I'm sure it is clear. Preventive action means we are taking some action if any contingency takes place. Even then, we are ensuring that our system will work perfectly fine. That means that all the contingencies are already considered during our preventive action plans. So a priori only, let's say for example, if you are talking about I gave an example for the medicines and viral fever. So let's say, obviously, if we take preventive action, like if let's say for example, in last class I mentioned about that if you are traveling by bike or two-wheeler, if you are just wearing a helmet, then you are only securing your head. But obviously there is a chance of getting my bones broken of my hand or leg. Obviously the chances are always there. So for that, I cannot ensure, like similar to a helmet, I cannot wear a suit or like a maybe if or a metal suit across the complete body, and that will be expensive to wear all that, and it will be inconvenient also. Inconvenient in the sense, if we talk in terms of power system, it will be technically infeasible, and economically also it will be very costly. And obviously, because we know that the possibility of damaging my bones or hand bones or the leg bones is very rare, right? Because not always, if you there is some situation like if you drive safely, then obviously there is a very less possibility or probability of getting your hands damaged or legs damaged. But obviously you cannot ensure that, because you can only ensure your driving, but you cannot ensure the driving of other people who are traveling in the road. Due to their mistake, you might also get damaged. So that's why we say that we take preventive action. Obviously, you can imagine from all those examples that it is economically and technically infeasible, because economically it will be too costly and technically it will be too difficult to manage the system with all those constraints in the preventive action plan. So that's why secure state is an ideal state. It's a dream state, but it is very rarely possible, and even not only rarely possible, it is even difficult to maintain a system in secure state. I hope it is clear to everyone. Right. Now let us see if there is some credible contingencies which might create some issue in the power system. Then we move. I'm going to a correctively secure state first. Let us go to the correctively secure state first. The alert state first. Now in the alert state, what will happen is, again, there is no limit violation at the present state, means at the state at which you are right now, there is no limit violation. But what happens if there is some because obviously there are a lot of components, there are a lot of contingencies which can take place, but if you take any one of the single credible contingency, there might be a situation that corrective action plans are not enough or sufficient to remove the post contingency violations. So that means when you move to an alert state, basically you need to ensure some preventive action plan for that particular contingency. So whichever contingency has led to this situation, you have to include that contingency into a preventive action plan. Preventive action plan means you have to be ready a priori, even before that contingency had taken place, that okay, if that contingency is taking place, I have already considered the impact in my preventive action plan. Clear? So corrective action plans are not enough. So basically in correctively secure state, what we saw that even if a contingency takes place, the corrective actions are enough. In the alert state, the difference between the block 2 and block 3 is that the corrective action plans are not enough and you need to include the preventive action plans. But here, another important point here in the alert state, because corrective action plans are not enough, and if let's say you missed a chance to take consideration of this contingency in your preventive action plan, that means you might have to go for load shedding, because that might be the only situation. So for example, let's say sudden load has increased with a huge value, and then obviously you have not considered that, okay, at this time there could be a load increase which can take place. Then suddenly what you will do, you have no option to again go for load shedding. Or what you can do, if let's say there are two parallel lines, let's say if there is a load of 200 megawatt, this line has a capacity of 100 megawatt, this line has a capacity of 100 megawatt. Then suddenly if this line is faulted and there is some issue on this line, then you only have 100 megawatt of line. And if you have not considered the situation while scheduling this load or telling this load to run at 200 megawatt, you do not have any option. You have to shed 100 megawatt here. You have to load shed. You have to go for load shedding. So this is a situation which is known as alert state, and generally whenever this situation happens in control center, they will get a alert warning immediately that, okay, there is something which is not normal, and system operator have to be on alert and immediately take an action. Clear? So you got the difference between correctively secure state and alert state. Now let us see the correctable emergency state. Can you guess what is happening in correctable emergency state? What is happening here in the fourth block? Okay. Can you think of what could be happening here?
It is the corrective emergency state. The long that happens when there are different between generation and evacuation. For example, this difference must be corrected.
I'm extremely sorry, I'm unable to hear you. There's a lot of background noise. Sorry. Probably is it for me or everybody else also cannot hear him? Can you try speaking once more? Couldn't get you, sorry. Anybody else, if you want to comment here? Sorry, probably you can just fix your mic, because I'm unable to hear you. It's really there's a lot of background noise. Yeah, it's clear, but some echo is there at back, or some probably robotic echo is there.
Yeah, no problem.
Probably you can just fix your mic, then it might be. Okay, anyways, let me just go ahead and tell you what exactly correctable emergency state is. Here, basically, we say that, okay, in the current state, we saw that in the correctively secure state, we told that at the present state there is no limit violation, and if let's say some credible contingency takes place which might lead to some system violations, then you can just take a corrective action plan to bring the system back to the correctively secure state. That was very clear to everyone. Now here what can happen in correctable emergency state is that there is naturally in the present state there is some system violations. In the present state, let's say currently whatever the system is running, here there is some system violation, either voltage limits are violated or line flow limit is violated. Then what you can do is, if you have already corrective action plans ready with you, already drawn action plans means we are talking about the corrective action plan here. So if a corrective action plan is ready with you, or obviously you have the corrective action plans, we say that these corrective action plans are enough to limit the violation. So already if at this state there is some system violation, let's say for example what I gave just now is that if there is a load of 200 megawatt, this can carry 100, this can carry 100, and I mentioned that if this can get violated. Now let's say you have a third line which can also carry 100 megawatt, but this is open, means obviously it is not operating. So you know that obviously as soon as this fault has taken place, you are at the correctable emergency state. What means correctable emergency? Because it is emergency and you have the limit violation, that obviously immediately as this line goes out, the power on this line will start flowing at 200 megawatt, but this line obviously cannot sustain that 200 megawatt. So what you can do as a corrective action plan, you can immediately switch on this line, and then immediately the power will be shared 100 megawatt 100 megawatt, and the limits or the line flow will come within the limits. Right. So this is the correctable emergency state, that at this moment there is some contingency which needs emergency operation, or some emergency, means the system operator has to be ready for some emergency action, and the corrective action plans are enough to bring the system back to the correctively secure state. So you got my point. Here, whenever in these two states, whenever I am saying correctively, the word correctively or correctable is added before secure state and emergency state, here I am saying that the corrective action plans, corrective action means just taking the medicine and making you again back to normal state or making you fit. So that corrective action plans are enough to bring the system back to the normal where there is no limit violations, right? But 4 is a special case. Here initially there is some limit violation, but after taking corrective action plans, you can easily eliminate all the limit violations. And obviously if you have, let's say this line is there, then obviously you do not need to shed the load. So that's why we say that no load shedding is required at this point, at this 4th time block. Fine. So alert state, you might need to take some load shedding, because in alert state you are not having this line. And in correctable emergency state, if let's say you are having that line, then you can avoid the load shedding and you can immediately switch on that line and then still operate the system without any limit violation. I hope this is making sense to everyone now. Now let us come to the 5th block, which is non-correctable emergency state. Now I hope now this will be very clear to everyone. Can anybody guess what will happen in non-correctable emergency state?
That the corrective action plans will not be enough to correct the limit violations that will be taking place.
Perfect. And what else? Because that is also not there in alert state. What is different from alert state then?
There will be no limit violation. There will be limit violation in the present state.
Okay, that is also there. Correct, agreed. What more? There is one thing which you are missing, which is very important.
Load shedding will be there.
Exactly. Perfect. Awesome. Nice. So load shedding is the only option remaining here. So obviously, as one of you said, that some limit violation will be there in the present state. Agreed. Now, even if we take the corrective action plans, we are not able to eliminate all the limit violations even after corrective action plans. So that means the initial design or the schedule what we have done at the correctively secure state, that was incorrect. Incorrect means because incorrect I mean to say here is, if we would have considered those contingencies in the preventive action plans, then obviously the corrective actions would be enough to do that. But we have not considered those contingencies in the preventive action plans. So now even the corrective action plans are not enough to basically bring the system back to the normal state. So even if we take the corrective action plans, there will be some few limit violations remaining in the system. And lastly, load shedding will be required to remove these violations. There is no second option here. You have to go for load shedding to eliminate those violations. So what I mentioned here, just to differentiate from the alert state there there might be or there may be a chance that load shedding is required, but not necessary. There could be some other alternative options available with the system operator, from which, or by using or by implementing that method, you can bring the system back to the normal. But in the non-correctable emergency state, you do not have any option. You only have option remaining is to go for load shedding. So there is no option remaining here. So I hope you got the idea. Clear? Now let us go to the last block, which is sixth block, which is known as restorative state. Can anybody guess what is happening here? Any thoughts? What is happening here?
Change the date. Do you hear me?
Yeah, there is a echo. You can speak a bit louder and closer to your mic. Then probably it will be easy to hear.
Okay. The restorative state is related to compensate that value that happened or that we compensate to return system to normal state.
So compensate means compensate what?
Voltage or amplifier, it depends on what.
No, not exactly. Means you are missing. You are very close, but compensate what? That is not clear. You are right. We have to compensate something, but compensate what? What is that which we have to compensate? Anybody else? Sorry.
Frequency of voltage?
No, because we are assuming the load generation balance is there in across the network. So that means there is no, if the load generation balance is there always, that means there is no issue of frequency.
Perhaps we should isolate the areas that contain the fault after we fix all the equipment or clearing the fault. We can restore that part of the network again.
Yeah,
normal.
Exactly. So whatever part of the system is actually has a fault, or because of fault we have went for some action which was necessary to bring the system back to not normal but back to a stable point. So stable is and normal is different. Stable means we do not want the system to go into a complete blackout or unsynchronism, out of synchronism. We want the system to still run, but some extreme actions we have taken. So, and that extreme actions was taken because of the faults which you are talking about, and that extreme action is just a single one, which is load shedding. So we did a load shedding in the non-correctable emergency state. So the restorative state is, or the compensation what you were telling, or rather restore what is the thing which we want to restore, that is the loads which we have already shed in the fifth block, or which is the non-correctable emergency state. So here as soon as you shed the load, immediately after that you move to the restorative state, and obviously as you have shed the load, as you have done the load shedding, then there is no limit violation in the present state. In this restorative state there is no load shedding, no system violation, right? Now do you see any something curious or something weird here? Do you see anything weird? I mentioned at the start that 1, 2, 3 blocks will have no limit violation, and I have mentioned that 4, 5, 6 will have limit violations, and I am saying here that there is no limit violations in the present state. So what I am missing here, and what I am or are there any limit violations or not? What is weird here? What is am I doing some mistake here, or is it logically correct, or what is missing here? Do you agree with me? I mentioned in the 4, 5, 6 blocks in the start that there will be limit violations here, here, and here, and here, here, and here. There will be no limit violations, but I'm mentioning here that there is no limit violations in the restorative state. Can anybody guess quickly? If that is true, then what?
Sir, in restorative state, we move from the limit violation to no limit violation. Initially, in the fifth state, there will be limit violation, but we will move to the no limit violation in this restorative state.
Yeah, so that means, are you agreeing that there will be no limit violation?
So there will
So
be no.
initially there will be limit violation.
No,
at the
initially
end,
no. I mean, at
band
the present, because we have
restorative
already done the load shedding here. So now we are here at the sixth state, and we are saying that there is no limit violations in the present state. Then why I am saying at the start that there is a limit violation in the sixth state, or sixth restorative state?
So there is a limit violation if we add the load demand that we have cut it or load schedule there.
Perfect. Exactly. So we are violating PD and QD. This is not within the limit. So this is the thing which we are violating. So naturally, PG, QG, PF, QF, V and delta all are within limit. Agreed. There is no problem. That's why I'm saying there is no limit violation in the present state. But naturally, to arrive at this state without any limit violation, we have done some load shedding, and that is actually the thing which is violating. Obviously, you cannot continue to work in the system after having load shedding. You have to restore that load. So that's why at the restorative state, till we complete the recovering or restoring of all the loads, and as soon as you recover all the loads, you move to the alert state. You are no more in the restorative state. So in the restorative state is a process where you are gradually connecting all the loads one by one and connecting it or switching it on one by one. So once you have restored all the loads, then you again move back to the alert state. You got the difference, what I was saying earlier and what I am saying right now. Is it making sense right now to everyone? Probably someone can mute. Probably there's a lot of echo if you're not speaking. Okay, so now once you have moved to the alert state, why I am moving, once you restore everything, why I am moving to alert state, why not to a correctively secure state? Can anybody answer this? From the restorative state, why I am moving to the alert state after restoring all the loads and not to the correctively secure state? Any guesses here? This might be a question from your side actually. That why we are keeping the arrow on the alert state and not on the correctively secure state.
So maybe we require some more load shedding.
No, we have already restored load. That's why we have arrived at alert state. So at the alert state right now, after coming, let me just delete all these. Let's just a second. Probably this. So we have restored all the loads. That's why we have arrived at the alert state. Even if that any one of the load is still not restored and it is still in the process to restore, that means we are still in the restorative state. We have not crossed that state. The system is still, we will call the system or we'll categorize the system as a restorative state, not as an alert state. So all the loads are already recovered. Now, why, my question is, why this arrow here is going to the alert state and not to the correctively secure state? What is, uh, why did I do that? Not I, but
Uh,
yeah, please go ahead.
because there is no corrective actions will be sufficient till we resolve that problem. Until that, we can go to the corrective state.
Awesome, awesome, nice, perfect, perfect, exactly. So basically, why we went from alert to this state is the reason why we are again coming back to the alert state, because there is some initial schedule P naught, QG naught, PF naught, QF naught, and PD naught and QD naught. This was the initial schedule. Not I am saying not means zero, what I am adding as a superscript, that is actually the initial schedule at which we have started from the correctively secure state. Now there was some issue in this schedule itself. That's why the corrective actions were not enough, and that's why we will again come back to the alert state, because we have to add some preventive action here, and to change the schedule there will be some additional actions. That's why we are not going to the correctively secure state, we are moving to a alert state. Do you get the difference here? And once probably the time passes, because time passes means because all these schedules, did I mention this or not, I forgot. In India, all these schedules are set for 15-minute time window. In Europe also it is 15-minute, in USA it is 5 minutes. So all country have a different. So India and Europe is on 15-minute market and 15-minute schedules, and this is USA. So USA is on a 5, even Canada is also on a 5-minute system. So they also they operate at so these initial schedules, they keep on changing in every 15 minute in Indian context, in European context as well. In US and Canadian context, it keeps on updating it every 5 minute. So basically this all process from restorative to alert state, you are staying at this alert state with this schedule only. And whenever the next schedule, which next 15-minute, whatever is the next 15-minute schedule is there you have to update that, okay, if we remain, or if let's say the next 15-minute schedule is also the same schedule, then the system operator knows a priori that, okay, this situation will lead to alert state, or this, if there is some contingency, we might go to the non-correctable emergency state. So we should take a preventive action, and then immediately he will update these initial initial values, and then it will move to the correctively secure state. I hope it is clear, or is it still confusing? So let's say I'll try to make it even more. Let's say right now it is 12 p.m. So 12 to 12:15, we were at some solution, let's say P naught. I'm not writing everything, just P naught. And you saw that this P naught has went from some contingency has happened, it went to the correctable emergency state, it moved to the restorative state, and it moved to the alert state. So right now the system is at alert state, and system operator knows that this solution P naught, and let's assume the PDQD from 12:15 to 12:30 is also the same, because obviously the load change for 15 minutes will not be much, it will be almost close to each other. So the system operator knows that this is in alert state, and right now it is 12:01. I'm talking at the correct time, at this time interval. So this is the current time. So the system operator knows that, okay, this P naught is the alert state. That means we cannot work if there is some contingency which takes place. So here, instead of P naught, he will schedule some P dash, which will include the preventive action for that particular contingency which has led to this alert state. And then after including that contingency, it will move to the correctively secure state. I'm just writing CS as a short. So this is block 2. right? So P dash, it will be there, the next schedule will be there, a P dash for the next time interval. So you got my point, the complete picture, how the system operator ensures all these parameters and information. So I'm not talking about mathematics here. Just I'll take 1 more minute and I'll close. I'm not talking about mathematics here. Mathematics will come probably 3-4 lectures down the line, and because I do not want to confuse you, because that is going to be a separate thing. And just keep this in your mind for a while, and probably 3-4 lectures or probably 5 or 6 lectures after, then we'll see the mathematics of it, because for the mathematics of those topics I need to explain some other things, some other basics before I move to that. So that's why I thought, okay, let us give the flavor here of how the operating states of power system work. Okay, any queries if you have, because I have already crossed my time. If you have any queries, I can explain.